Today we will be talking about applications of determinants to see in what ways we could possibly use determinants and maybe what kind of interpretations they have. The first application of determinants for today will be Cramer's rule. Now, I'll explain Cramer's rule on a 3x3 setting, although it works for n by n situation, but it's just not very efficient to use. The goal of Cramer's rule is to solve ax equals b. So the standard system of ax equals b can actually be solved through determinants. I will first sort of show you how to solve a 2x2 system on a particular example, and then I'll explain where the rule comes from and how to use it. I would ask you perhaps to use it on a 2x2 or 3x3 system, maybe a 4x4 if there are enough zeros in the matrix. But beyond that, Cramer's rule is actually not efficient. It does, however, reveal an idea on how to use the determinant of a matrix to find its inverse. We will do that in the second video. So Cramer's rule, useful for small systems, immediately finds us what x needs to be, especially if you have a 2x2 system and not just in linear algebra. The idea of this course is that it will be useful in other courses that you take, whether you're in engineering or economics or business, or something completely unrelated to mathematics, could be social studies, where you just need to solve a 2x2 system. Determinants come into play in a very quick and elegant way when the system is sufficiently small. Okay, I'll start with an example. So let's say we have this system. We have the matrix 3, 4, 5, 6 times the vector x with components x1, x2 equals the vector b with components 2, 4. Now, it's nice to be able to solve this right away, and I'll just explain immediately what Cramer's rule, how Cramer's rule gives us x1 and x2 just from these 6 numbers as a formula. So here's how it happens. x1 equals a ratio of 2 determinants. In the bottom, I have so remember, this is the matrix A, and this is the vector B. So in the denominator, I have the determinant of the matrix A. Notice the vertical line, so that means I'm talking about a determinant. And I'll have a different determinant on top. Okay. And x2 will also be in that form. So there will be a determinant on top and a determinant on the determinant in the denominator is A, determinant A. Okay, so far so good, I hope. Now, where does the vector B, I should have a lowercase b here. I just want to change the color. So this is 2, 4, okay? Now, the vector B, when I'm trying to find x1, will go into the first column of the numerator determinant. It will be here. And when I'm finding x2, it will be in the second column. It will replace the second column of A. And the rest will be just like in the denominator. So I have a 4, 6 here that comes from A. And then I have 3, 5 there, comes from A again. So I replace one row at a time. One column at a time with B. If I'm trying to find x1, so that's the first component, x1 corresponds to coefficients that are stored in the first column of A. For x1, B will replace the first column, the second column will remain the same. So you see this column and this column is the same. the first column is replaced with B. So again, this is A. Now we're looking for x2. The coefficients of x2 are in the second column. We will replace those with B, and that's it. Now all you have to do is actually solve the determinants, and you have found what x1 and x2 need to be without using elimination. So what is the determinant in the numerator? We have 2 times 6, 12, minus 4 times 4, which is 16. In the denominator, we have 3 times 6, which is 18, minus 4 times 5, which is 20. And so we have negative 4 divided by negative 2, which is simply 2. And for x2, well, we know the denominator is again negative 2 because it's the same determinant. And the numerator will be 3 times 4, which is 12, minus 5 times 2, which is 10. And so here we get negative 1. So the vector x is 2, negative 1. You can double check that this is really so. So it tells us to take 2 times the first column minus the second column and see if that will equal B. We can quickly do that. So if we take 2 times the first column and negative 1 times the second column, let's see, 6 minus 4 is indeed 2. 10 minus 6 is indeed 4, so that is correct. Now, as you might imagine, if we have a 3 by 3 system, well, that vector B, so if our system has 3 columns here, 1, 2, 3 columns, then the vector x will have 3 components, x1, x2, x3. And so B for x1 will replace the first column. For x2, it will replace the second column. For x3, it will replace the third column. But the idea is exactly the same as here. Now, with that, let's see why this works. Now, it's a very interesting sort of very basic key idea. I'll explain the key idea of why this works, why Cramer's rule works on a 3 by 3 matrix. Of course, this can be extended to n dimensions, although as I mentioned, it is not a very efficient way. Remember, determinants, it's very nice to write this. It looks great. I didn't have to do any elimination. It's a formula I can remember. But actually, it's a formula if you have a 2 by 2 matrix and the determinant of a 2 by 2 matrix. That's easy enough. However, if you already go to 3 by 3, we also have a formula, but there are 6 terms in the sum that we have to compute for each determinant. And once you go to higher sizes, the determinant is actually not that cheap, computationally speaking, to compute. So not a great idea, not very efficient if you go to bigger systems. Okay, so how do we want to solve? Remember, we are solving AX equals B. Let's say A is 3 by 3. So we have our matrix A, which is 3 by 3, times the vector X with components x1, x2, x3, equals the vector with 3 components b1, b2, b3. Now, here is the idea. So I want to find x1, then x2, then x3. Let's look at the following matrix. So here I will have A again. Now, instead of a vector, I'm going to take, so let's say I start with the identity matrix. When I take the product, I'm going to get A. So I'm going to get a 3 by 3 matrix, right? In fact, let me do something else here. Instead of, so this will still be the matrix A, but let me represent A through its columns because we're replacing columns. So I want to be able to see that. So by maybe here, A1, A2, A3, these represent the columns of A. Okay, these are not components in a vector. These represent the columns. So if I were to multiply by this matrix, I will get A again. Obviously, that's not what I want to get. So let's look at the idea of replacing the first column here with the vector x, with x1, x2, x3. What are we going to get when we multiply? So the multiplication approach that I'm going to take will be matrix times column. So this matrix is the matrix A. When I multiply it by the vector x, I'm going to get the vector b, because that's exactly what I have in the rule. So I know that the first column is b1, b2, b3, or just the vector b if you like. So it's important to visualize the components of x, not so much the components of b. So I know that I'm getting the vector b. I will replace that with just one letter, which is the letter b. And here as well, it's just going to be easier for us. Okay, now I'm going to multiply the matrix by the second column. Now I want you to visualize this multiplication as a linear combination. So I have a 0 here and a 0 there. What does that linear combination tell us to do? Well, it simply says take the second column of A. If you multiply this matrix by this vector, all you get as a result is the second column of A, because it says take 0 of the first column, 1 of the second, 0 of the third. So actually the result of that matrix by vector multiplication is A2. And then if you take the matrix times the third column, you're going to get A3. Okay. Why do we care here? Let me call this right-hand matrix B1, capital B1. Why B1? Because I wanted to remind me that the vector B is in the first column. Now, if I take determinants, so I have a product of three matrices, of two matrices on the left-hand side equal to another matrix on the right-hand side. I know that the determinant of a product is the product of determinants. Now, the determinant of this matrix is just determinant of A. The determinant of this matrix is the product of terms along the diagonal. So the determinant here is simply x1. The determinant of that matrix is simply x1, and then the determinant here of b1 is the determinant of b1. So what I have from the product is that the determinant of A times x1 equals the determinant of b1. From here, I have x1 equals the determinant of b1 over the determinant of A. Now, as you might imagine, the same trick works for us to find x2. I'll only show you for x2, and then you will be convinced you don't have to see it for x3 as well. So let's write that matrix system one more time, but now the vector x will go into the second column. So I have the matrix A again, represented through its columns. And now I multiply by a matrix which is obtained from the identity by replacing the second column with x1, x2, x3. And then 1 here. Now, as you might imagine, if I put why the third one works easier, or why it's really the same as the first example, because if I have here x1, x2, x3, and this over here is 1, then I have an upper triangular matrix and the determinant is simply x3. So that's easy. The trickier part is over here. Why is this determinant equal to x2? Although not that difficult to see. Anyway, when we take the product, when I multiply A by the first column of the identity matrix, I'm going to get the first column of A. When I multiply the entire matrix A by the vector X, I'm going to get the vector B. And when I multiply A by the third column of the identity matrix, I'm simply getting the third column of A. Okay, so this is clear. The only question is, so this will be the matrix B2, the determinant of A. So what we want to say here is determinant of A times x2 equals determinant of B2, and so x2 is the ratio determinant of B2 over determinant of A. Just a quick reminder as to why we get this to be the determinant. So what is the determinant of this matrix? There are, obviously, you could just try and solve it and see that it is x2. Multiple ways to see it. One way could be we could use expansion along the first column. So we did that yesterday. That would be, so expansion along the first column really just means 1 times the determinant of this smaller matrix. And then you see that the determinant of the smaller matrix being lower triangular. So this determinant, the big determinant, is equal to this smaller determinant. And that is a lower triangular matrix. So you see that the determinant is x2. Another way to see this is if you want to carry out elimination. So this would be the first pivot. Everything underneath it is 0, so we're done. Then we go to the second pivot and we eliminate underneath. Because we have zeros here, we know that this 1 will not be affected. So x3 will be eliminated, but 1 will stay as is. And so again, we will get an upper triangular matrix. Only that part matters. Again, you get x2 to be the determinant. One could also do expansion along the second row. If we did expansion along the second row, we have to be careful with the sign. So we have plus, minus, plus. So we would have x2 times the determinant that we obtained from removing the second row and the second column, which is the determinant of the identity matrix. So again, we get that the determinant is x2. So multiple ways to get the same thing. And that is all I have to say about Cramer's rule.